Hi students, this video is on enthalpy and energy changes. You might have noticed if you've ever been sitting around a campfire, releases a lot of heat, right? And how exactly does that process work? What is fire exactly? Well, we're not going to answer all of that today, but we will talk a little bit about how does the energy stored in wood get released in a chemical reaction as heat, and how exactly that process occurs. So before we get there, we really want to be thinking about the idea of chemical bonds. We have to go back to the chemical bond. If you remember, a chemical bond holds energy, okay? That the bond between two atoms contains what's called chemical potential energy. And when you have a bond between atoms, that's basically what's happening. What's often not known, though, is that every bond is a little bit different, and every bond holds a different amount of energy in it. Now, you might expect that a single bond between two atoms might not be a very high energy bond because it's just one bond. You might look at a triple bond like the one that's between nitrogen here and say, okay, probably a pretty high energy bond. But actually, the opposite is the case. Well, why would a triple bond be a low energy bond and a single bond be a high energy bond? This goes back to the fact that bonds are stored energy, chemical potential energy. And potential energy, it is basically from the idea that it's a potential to do work. So the ability to do work and perform a task, that's what potential energy is all about. It's the same in physics as it is in chemistry. But the idea is that some bonds have more of that potential energy than others. How do you know the difference between a high energy bond and a low energy bond? Well, a high energy bond is actually less stable than a low energy bond. So this one up here is unstable, or has a lower stability at least. And then this one down here has a high stability. So the difference between the two is that one is unstable or less stable and the other has a high stability. Now, it's not about to fall apart or anything, but it's eager to find a more stable partner to basically create a stronger bond between if it can. And so the higher energy bonds will have a greater potential basically to react between other types of chemicals. If given the energy and ability to do it, they will try to do that more than a lower energy bond like nitrogen down here. And then a final point about that is just to put a name to this. The energy required to break and to form a bond, we're going to look at a bunch of these values. It's called its bond enthalpy, and that's kind of a strange word. It sounds like energy, but it's not. It's a little bit different. Enthalpy. And this has the idea of stored heat, or the ability of a system to do some heating or do some work. If it's a high amount of enthalpy, then that system can do a lot of work. If it's a low amount of enthalpy, that system of chemicals has a low ability to do work. So how do we actually quantify this energy, this enthalpy idea? Well, enthalpy is written as H. We'll see that a lot. The letter H is measured, is a measured amount that we use, and the units are kilojoules per mole. The joule is a unit that is a standard unit for energy, but the particular units for enthalpy are kilojoules per mole because it has to do with how much energy a mole of a substance it would release if that mole either bonded or was broken apart. And each bond, as we said earlier, has its own particular strength and its own, so therefore its own enthalpy value. So if you look over here, you've got bonds between carbon and hydrogen, carbon and carbon, double bonds between carbon and carbon and oxygen. So lots of different bonds, and they all have different numbers. I think there's 12 different things here, and this is of course a small sample of all the bond enthalpies out there. And the basic idea is that when you break a bond, we're going to absorb energy into the system in this process. When we form a bond, we'll release that energy to the system and actually out into the surroundings. The key thing, though, is that no matter which way you go, both values are actually equal. So if I break this C and H bond right here, I'm going to require 413 kilojoules for every mole of CH bonds that I break. If I make a mole of CH bonds, I'll actually get back 413 kilojoules for making a mole of those bonds. So it works either way. So first we're going to look at this visually, and then we're going to try to envision this a little bit more mathematically. So to look at it visually, how can we model this visually? First, let's draw a graph, and let's put reactants and products on this graph here. And if we put the reactants up at the top of the graph here, where H is high, and the products down here at the bottom here, where H is low, you'll see it's just like we're kind of discussing with fire, where you've got products of, perhaps ash or, charcoal or whatever is going to come out of the wood. And that's going to have a very low enthalpy, but the reactants, the wood, are going to have a much higher enthalpy before they're burned. And then once the reaction starts, then the reaction goes what we would say downhill, and it actually releases energy in the process in the form of heat. And that heat goes into some kinetic energy of motion shaking the molecules around, and they will have an increased heat as a result of that. And so we call this an exothermic reaction. Why? Because the products have less enthalpy than the reactants, and we'll get into this in a moment, but the value of delta H will be negative, okay? So we'll see what we mean about that. But just briefly, to look at it one other way, reactants on top and products on the bottom, the difference between the two is this concept called delta H. It's that the reactants have a higher level of enthalpy, the products have a lower level of enthalpy. In the case of wood, much higher level of enthalpy in reactants because they can burn still, but once they're products and they're ash, there's no real ability for ash to do much work anymore. So we'd say the enthalpy of that system is very low, and their bonds are actually very, very stable comparatively. So let's solve this sort of from a mathematical perspective. The equation that you're going to want to know is delta H of reaction is equal to the enthalpy of the absorbed energy here, and the released, minus the released energy. So you'll be able to look up values for these two and basically calculate how much change in enthalpy has occurred. I'll show you what I mean. Let's try to combine water, hydrogen and oxygen, to make water. So let's make water. To do this, we'll figure out, is this an exothermic reaction or an endothermic reaction as well? So what we'll do is we'll combine those two, and we'll look at the amount of energy that's absorbed in the process. Remember, absorbed means it's the amount of energy that goes into the reactants. So the absorbed energy goes in here. The released energy comes from here, because as I break the bond, I absorb energy. As I form bonds, I release energy. So that's the difference between the reactants and the products, is that they're that you get energy back with the products, you require energy with the reactants. So now I'm going to figure out what those numbers are going to be. So first I have delta H, and I need to look up the H of the absorbed value. So absorbed value is going to be up here with HH bonds in 436 kilojoules per mole of every HH bond that I have. I have 2 moles, so I actually have to multiply 436 times 2, and then I need to add it to the oxygen value as well, which is found here, 495 kilojoules per mole for that one. And if I add those two things together, you'll see I'll get this value here, 1367. So that is the amount that was absorbed or required to break the H2 and the O2 bonds. I just summed them together. I added them all together. And then I add up the amount of energy that's released when I make these OH bonds. Now you'll see the number is 463 over here, but there's actually 4 of those bonds happening because in any given water molecule, there's 2 OH bonds. And I see that I have 2 moles of H2O in this reaction, so I have to multiply that number 463 by 4. And when I do that, I get the 1852 that's right here. So what is the final value of this? Delta H is 1367 minus 1852, which is negative 485 kilojoules per mole. And that negative value tells me that it is exothermic, because I know that anytime I have a negative delta H, it's going to be exothermic. Let's try this with an endothermic reaction. So I'll draw my graph again, and then I've got reactants down at the bottom because I have a low amount of enthalpy in the reactants. I have products up at the top, they have a higher enthalpy. Let's see what happens when the reaction occurs. I go up the hill. I actually have to put energy in, just like if I was running up a hill, I have to put in energy in order to do that. And then eventually I'll make my products. You have to go over the hump a little bit more than just going right up to the line, but that's actually beyond the scope of the lesson here. But regardless, in the end, the products are going to have more enthalpy than the reactants, and delta H will then be positive. Let's see how that makes sense mathematically. We'll look also at just the visualization here of delta H being the increase from reactants to products, and this is going to be a positive delta H, obviously, because I start off with a low enthalpy, I go up to a higher enthalpy. If I started off with 500 kilojoules and I end up with 1,000 kilojoules per mole, that's going to be a positive gain of enthalpy. So let's see how that might look. So I've got the same equation, but actually flipped it around. I put the products as reactants and the reactants as products. This is splitting water into hydrogen and oxygen. So I'll put my values in just like before. It's the same numbers, but they're in different order. And so now my answer is 485 kilojoules per mole, but it's positive. It's positive because I flipped everything around. So you'll notice that it is the same numbers, and then when I flip it around, it becomes the positive value instead. And what's interesting about that is that means in order to make this reaction happen, I have to put energy into it. And for every mole of, actually it's technically every mole of oxygen I produce, but for every mole that I'm doing this reaction, I need to put in another 485 kilojoules in order to keep producing. So that's why this is a textbook endothermic reaction, because I have to put energy in. Okay, so did you learn that bond strength and stability are basically how we determine how much energy will be required to make or break that bond? That has to do with those concepts. And exothermic and endothermic reactions basically are modeled. We can model them on a graph. And what kind of graph do they look like? Could you match the graph with the type of reaction? And delta H is used basically to determine whether a reaction is going to absorb or release more heat overall. If it's positive, it's going to be endothermic. If it's negative, it's going to be exothermic. I hope that was helpful.